So our presentation is going to be on nanoparticles in solar cells. And today I will be sharing this presentation to you with my partners, Kaylee and Corbett. On this slide in particular, on the bottom right, there's an electron microscope image of nanoparticles. Okay, so moving on to the first slide, which is us answering the question of what type of nanoparticles were used. The nanoparticles that were most commonly used were gold and silver nanoparticles specifically. This is because they are the most widely used materials as their surface plasmon resonances are located within the visible range. This makes them interact more strongly with the peak solar intensity. The concentrations that they were used most commonly with were 1%, 5%, 10%, 20%, and 40% respectively, with gold and silver nanoparticles at an original size of approximately 100 nanometers. However, after spinning/annealing, some nanoparticle sizes will agglomerate to large nanoparticles at sizes of around 100 to 250 nanoparticles. This verifies that broadening the shape of the resonance wavelength is caused by random distribution and the non-uniformity of the size of the gold nanoparticles, which causes the particle density to increase with the gold nanoparticle concentration. It was also found that at higher concentrations, the nanoparticle effect, like the efficiency of the nanoparticles on the solar cells, actually decreased. So the smaller the nanoparticles and the lower the concentration, the more effective that they were for the most part. The silver and gold nanoparticles were able to be randomly distributed more often via spin coating, which again broadened the resonance wavelength of the transmittance, which is favored in solar cell applications. Also, metal shadowing competes with the light scattering of the solar cells, which is why larger concentrations of these nanoparticles were less efficient within the solar cells because the shadowing of the metals competed with the light scattering.
So moving on to the second question of what is the application? The utilization of solar cells to harvest inexhaustible solar energy is costly and can be innovated further for maximum efficiency. So we can do this by incorporating silver and gold nanoparticles into multicrystalline silicon solar cells and copper indium gallium diselenide 6 solar cells. This increases the efficiency enhancement of the MC silicon cells by 5.9% and 4.8% respectively. And it increases the efficiency enhancement of the SIG solar cells by 1.2% and 1.4% respectively. Additionally, particular methods for incorporating the metal nanoparticles can be simple and low-cost expense additions. Specifically the method of metal nanoparticles on the surface and spin coating, which makes them ideal candidates for improving solar energy and solar energy harvesting. So there are actually other known methods for increasing the solar cell efficiency, and this includes the mentioned spin coating, but other methods include e-beam lithography, thermal evaporation and annealing, chemical bath deposition, and nano imprinting, etc. We are focusing on spin coating because it is a simple and low-cost method. And in the table below, we have the nanoparticle concentrations and their percentage of efficiency enhancement. And so as you can see, the 5.9% and 4.8% and other values are in the table. And like Aurora stated, there is a certain threshold of where the concentration yields the most efficiency enhancement. Moving on to how nanoparticles are involved in the application, incorporating the silver and gold nanoparticles causes an effect known as surface plasmonic effect, and this redirects the light in the formation of the waveguide mode, which is then absorbed in these semiconductors. This causes the photocurrent enhancement and also causes a localized surface plasmonic resonance effect of the metal nanoparticle, which causes high near field intensities. And this also enhances the absorption. So To sum up, metal nanoparticles scatter incident light over a range of angles, and this increases the path length of light and the absorbing semiconductor of the solar cells. And thus the efficiency of the absorption is increased.
Yeah, so then moving on to the last question, which is what current technology or method or process is this new process improving upon? And so currently we have solar cells all over the place, bringing in solar energy to try and fight climate change through growing the share of renewable energy that we have. And solar cells have the potential to make a large contribution to solving the fossil fuel shortage problem, as well as making a dent in climate change. But experimental results reveal that the incorporation of gold nanoparticles in MCSI solar cells outperform silver nanoparticles, and that incorporation into CIGS solar cells yield a higher enhancement of the photocurrent and thus higher absorption, which just makes those solar cells even more efficient and effective at bringing in the renewable solar energy. As the gold and silver nanoparticles are deposited via the low-cost spin coating process, this favors solar cell applications. Such recent improvements in solar energy systems, such as scientists developing new materials and innovations, specifically the incorporation of gold nanoparticles into CIGS solar cells, will help to increase the efficiency of solar energy harvesting and alleviating energy shortages. Like I said before, the solar cells are already a part of our infrastructure, and they're only going to become a larger and larger share of the energy market. And so it only makes sense that these innovations will come along to help make these solar cells more efficient and effective at absorbing that solar energy. So in conclusion, solar cells have that potential to make a large contribution to solving fossil fuel shortages, as well as making a noticeable dent in the climate crisis. And lastly, we just have our references, which you can see. It's where we get our graphics, our pictures, as well as all of the research that we use in this presentation. Thanks, and Gig'em.